Hello again. In this video we will cover short circuit calculation example. Short circuit will appear on an electrical system on any voltage, and industrial or utility, it doesn't really matter. They are all prone to short circuits due to a fault to loads and to lines. A short circuit is a random event, and therefore there are many problems of how exactly to predict it and what size and shape will it have. One of the main methods is the MVA method, and that MVA method is basically based on the size of the component hanging on the line. In our example, what we have in front of us is an industrial system, electrical systems, with an incoming line where the transformer, utility transformer, is contributing 250 MVA, one bus 33 kV, another bus 11 kV, 6.6 kV, and the bottom line, which is 400 volts for low voltage equipment and motors. We have two motors here, each one of them with a different internal impedance, and that is what is important for short circuit. So this one has 17% of the full impedance during a short circuit. This group of motors will have 25%. On that bus we have that transformer, secondary, and a group of motors with 17% internal impedance. This bus will have the secondary of the incoming transformer, the primary of the outgoing transformer, a standby generator, and a motor. Each one of them has a different internal impedance during a fault. The main line, the top line, is a bus that will see only the primary of the transformer sitting here, the 10 MVA transformer, which is in this case 9% internal impedance during a fault. Each one of them, in case of a short circuit, regardless where the short circuit is, will respond differently. And it is based on its MVA size and its internal impedance. When there is a shock, when there is a short circuit, a shock wave is coming and retreating. That shock, that hiccup on the network has two effects. One that goes all the way down from bus to bus, from unit to unit, and then coming back to its origin. We have to count for both of them. The one that goes down and the one that will respond and go back. So each generator, transformer, motors, has its own size and internal impedance. As we said, each one of those short circuits might find itself on a utility, generators, motors, transformers, anywhere on the system. The way to calculate the effect and the size of the component, like the transformer, generator, motor, during a short circuit and its burden on the network, is being calculated based on this calculation. For cables and reactors, this is the way. For generators, this is the way. Transformers, it's the MVA divided by the internal impedance. So in most of the cases, we can see the effect during a short circuit as its total nominal MVA divided by its internal impedance. And that's what we will do for each and every component. So we take each and every component and we calculate its effect based on the size and internal impedance during a short circuit. For the main transformer right there, it will be 10 MVA divided by 10%, which is 0.09. So during a short circuit, the transformer will behave like 111 MVA for a very short time. All those calculations are in effect for the first 2-3 cycles during a short circuit. And that's the way we continue for each and every component. Like for the generator, standby generator, we take its 3 MVA and divide it by 11.3%, which will give us 33 MVA during a short circuit. And so on and so forth, we continue on and on and on from each and every component to the next one. From each level down, down, down to the bottom line, to the end user. This is the end user. We will use those values calculated here during our next calculation. Now we are looking at the transformer which we already calculated its primary effect, and the primary effect is 10 MVA divided by the internal impedance, which is 9%. It is 111 MVA during a short circuit. The two sides, primary and secondary, of the transformer is behaving like impedances in parallel. In total, the total impedance of two impedances in parallel are 1 divided by 1 over 1 plus 1 over the second one. So the incoming MVA is 250 MVA, and the transformer secondary is 111 MVA. 1 over 250 plus 1 over 111, 1 over everything, will give us the feeder contribution down into the next bus, the 11 kV bus. And that is 76 MVA. That superposition that is being done by the transformer, the incoming MVA capacity and the outgoing MVA capacity that behaves like impedances in parallel, will be the way we calculate for each and every transformer. And we are going from the top down, 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 down. We continue on. From that bus down, we will have the contribution of the generator, of the collection of motors sitting and connected to that bus, and the incoming effect of the upper transformer, which we already did. And we add them together, the 76 MVA that we calculated here, plus 35 MVA, plus 29 MVA from the motors, will give us 141 MVA on the short circuit first 2-3 cycles. That is the shock that the system will see. Then we go farther down and we see the contribution to that bus. And that will be the 141 MVA we saw before, plus the 5 MVA divided by 7% internal impedance, which is 71 MVA. The total is 47 MVA, and that is the contribution of that transformer. We continue that way down to see the effect on that transformer. And we calculated to the effect of the feeder 87 MVA. Then we take the total contribution on the 400 volts bus, which total to 24 MVA. That 24 MVA during a short, let's not forget, during a short, will be distributed between the two motors. One of them will be 10 MVA short circuit, and the other one will be almost 14 MVA during a short. Since we finished the calculation going down, 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 down to that user level, we know the effect. It's hitting the bottom and coming back up. And that will be the total short circuit on the 400 volts bus. The current that we can expect here will be the MVA divided by the voltage multiplied by the square root of 3 due to 3-phase, which tells us that it is 40 kiloamps during a short circuit. All that was going down. Now we are going back up. We reverse direction. When we go up, we see the effect of those two motors back on that transformer, and we repeat the same calculation, collecting all the currents and MVAs going up. The total of the two motors, as calculated before, 1.7 and 2.4, altogether 4.14 MVA hitting back as a backsplash into that transformer. That transformer will see the shock coming back, being added to its own capacity, will give us altogether 3.7 MVA. Then will be a collection of effects of that transformer and that motor into that transformer. Adding the two together, we are having 43.7 MVA coming into the secondary of the transformer. Continuing on, we calculate that way all the contribution coming up, going into that bus, coming up. Next we will collect that effect, and that effect together with the transformer, all going into the secondary of the first transformer. And the total will be 168.8 MVA. And of course, divided by the voltage, in this case 11 kV multiplied by the square root of 3 due to 3-phase, will give us almost 9 kiloamps on a short circuit. That will total into 92 almost MVAs going up. Together with the size of the transformer, the shock going into the 33 kV will be, together with the size of the transformer, 50 MVA. Divided by the 33 kV and the square root of 3 will give us about 5.125 kiloamps during a short circuit. And that will give us all the information that we need in order to specify circuit breakers and equipment on each and every bus. The main piece of information we need in order to order a circuit breaker is its current. What the circuit breaker is supposed to break, separate. And those are the currents that it's supposed to separate under a short circuit. And that's why we do the calculation. There are software packages that will do the job for us much faster and much more accurate, but internally, that is exactly what it is doing. So thank you for watching, and God bless.